Okay, good morning. Welcome to
FamilyMath number 886.
FamilyMath886. So yesterday I saw, shared on Twitter, this amazing Fourier transform program written by Jez Swanson. Hopefully that's how you say the name. And you played around with this for, what, 10 minutes this morning? All right, so talk to me about what you saw and what you thought was interesting and whatever you want.
Well, it's interesting. This first thing is interesting, how it can make us using just circles. It draws a bunch of circles that are related to each other, and then those circles can draw a pattern just by rotating around themselves. It draws the hand again.
Cool.
So, the first thing he says here is that you can split periodic waves like this, or any they don't really have to be waves, they can just be anything periodic, into sine waves.
Okay.
So here's some weird wave, and here's how it splits it into sine waves.
Yeah, so this is a fascinating aspect of what's called Fourier analysis. So you have a wave up at the top here, or it was up there as well, and it's not obvious at all what that is. But amazingly, it can be broken apart into these two waves that are very easy to understand. And in fact, I think, is this the one where it allows you to play them?
I think that's down here, yeah.
All right, so play the full wave.
So our full wave sounds like this.
Okay, and then a high frequency. Now, of those two waves that it's made up of, which one do you think is the high frequency wave?
It's this lower one.
Okay, why is that?
Because it has a shorter wavelength.
Okay.
Which is going to result in a higher frequency.
Nice. All right.
And then our other one.
So the complicated wave at the top, scroll up just a little bit because it just went off camera. The complicated wave at the top is composed of those two prior waves. Does that remind you of anything else in math that you've encountered?
It's kind of like function composition.
Yeah, it is a little like function composition, but function composition is f of g of x, not f of x plus g of x or f of x times g of x, but it is a little like function composition. But I was thinking about how you break something complicated apart into smaller pieces that are easier to understand, that it's made out of.
Like factoring polynomials would be an example of that?
Yeah, factoring polynomials, factoring integers into primes. And as I've told you over the years, factoring integers is one of the most difficult problems that there is. But it turns out, almost miraculously, that breaking up these waves into their components actually isn't that hard. So okay, so keep scrolling down. What else did you think was interesting?
So you've got stuff like this where you wouldn't really think of this as a wave.
Our cat is exploring the computer right now. All right, you wouldn't think of that as a wave. That's an interesting thing. So why not?
Well, it just looks like rectangles. It just looks like you've got the top of a rectangle and the bottom and the top. It's periodic, but it doesn't seem like that you could make the set of sine waves. But it turns out that you can. But it is infinitely many sine waves.
Nice. Okay.
And then down here, he shows how as you keep adding sine waves, or here's taking away, but here as you keep adding sine waves, it gets closer and closer.
Yeah, and play with the bar, so you can actually control this one, can't you? Or is it further down where you can control it? So you start constructing that thing up top that's called a square wave. And you're right, you do need infinitely many, but what do you see as you go along here?
Well, here we're not that far along, we already look pretty close to the square wave. So it's kind of the first couple that are going to really define it, and then these last lot of them are going to kind of flesh it out.
All right, and what do you notice here as you've got nearly infinitely many?
Well, where it's almost vertical, you've got it dips down and then goes up, and then goes down, dips down, and then goes back up. I lost it. There we go.
Okay. All right, so keep going.
So we can play this wave actually.
Alright, so there's a square wave.
This is like a chord of infinitely many notes.
Yeah, it is.
And it says down here that you'll notice that the first few waves are the ones that make the biggest difference. And then we need the smaller waves to make the wiggliness flatten out.
Nice. Okay.
So then I drew something really complicated
Alright.
to see if this actually works, and it in fact does work.
Huh.
And these are the waves that you need. So you start like this. It was interesting that these are sine waves. This spiky thing is sine waves.
This one down here?
Yeah.
Huh.
And then it slowly draws out the spikes that I have here. This one, if you're halfway, you can't quite tell, but
Can't tell what?
you can't really tell what it's gonna look like.
Uh-huh.
You kind of have to go all the way out.
I see.
And even then, even here, it's not looking
I
quite.
don't know. You got your 2
Mhm.
peaks there. Down. It's not bad. Go halfway again.
So,
Back to here. So you don't like this version of it?
well, like I can't see like this flat part. I mean, maybe it's here.
Yeah, actually scroll all the way to the end. Let's see where it is. Okay, so there it is.
Yeah.
And now scroll down to the middle. No, you're right. It really does. It doesn't appear. And so you need a lot. So why do you think you need so many on this one, whereas even on the square wave you only needed maybe, I don't know, 5 or 10? You started really seeing the square wave.
Well, it's because you have these little spikes. Because the sine waves don't naturally make pointed edges.
Uh-huh.
Like these. I mean, with the square wave you had 90-degree corners, but here you have like 5-degree points, which I
Cool.
guess makes it a bit hard to make.
All right, so tell me one last thing you saw in here that you thought was interesting, and then we'll be done with our talk.
Well, the 3D version of this is also pretty cool, which is going back to what he had at the beginning, where you make circles. They're called epicycles, and they look like circles from head on, but they're actually a bunch of the three-dimensional equivalent to a sine wave. And then you can draw pretty much anything you want to draw.
What did you draw?
I was trying to break it, and I tried to draw this something with really jagged edges.
Oh, okay. That's cool. And it has the same thing. So let's.
So this is using. So if you use this one, actually does it pretty fast. If you use only one circle, use a circle, and then kind of go. And here you can already see the shape of it.
Nice. So how many is that in there? Oh, that's still like 10, isn't it?
Yeah.
Okay. Well, still, it does. You're right. It goes really quickly. And what do you think about the sort of midway convergence here?
Well, it's sort of halfway. You're basically there already. Like I really can't tell the difference between this and this.
Okay. And how about right in the beginning, the very first approximation? What do you think about that?
It's not great.
It's not. Well, how about for just the first approximation?
It is pretty. Well, it's a bit small for a first approximation.
Okay. So it's a little small. So what's the second one, or sort of the very next one?
Next one, probably it's 2 circles like that.
Oh, okay. All right. So, what do you think is better? If I showed you the single circle for this or 2 circles, what would you say?
Well, you've got the X direction kind of down. You can, oops. Can't get it to stay there.
It's all right.
But you've got the X direction down. It's about the same width.
Okay.
And like here, you can already kind of see this little dip in here.
Yeah, and it's interesting though. This corner there isn't appearing yet. How long does that take to appear?
There, you can kind of start to see it.
Neat. So, what do you think? Is this a subject you'd like to learn more about?
Yeah.
Okay. Well, turns out it's related to calculus, so it's good that you're studying calculus now. All right. Good job, hon. High five.